Hello everyone, Dr. Data Science here to teach you data science methods and tools today, tomorrow, and beyond. In this video, we talk about building a simple neural network from scratch with PyTorch. So as you can see here, we are going to use these basic building blocks and talk about what each step means and how we can put them together to solve the machine learning problem that we have. And this is extremely important because these are building blocks for more complex and sophisticated problems that we are going to talk about them later on. So please don't forget to like and subscribe to make sure you don't miss any of those videos. In this video series, as the name suggests, we are going to work with the Dive into Deep Learning textbook. And the reason that I have chosen this one is because first, it is open source and free to use, so you can just go to d2l.ai and you should have access to this textbook. And this is truly a nice textbook with a really nice balance between code, math, and discussions. And you have access to all the implementations, so you can start replicating these experiments either using Jupyter Notebook or Google Colab. And this is something that very valuable in my opinion for learning about deep learning. Before we start, we need to look at gradient descent, and I have some videos that have discussed this before, but I'm going to very quickly discuss the main ideas that we need for this lecture. So in order to understand gradient descent, let's say we have a simple problem that we have 3 data points and we have the XY coordinates. And the goal here is to find the relationship or the connection between X and Y. Obviously here these 3 points are on the 45-degree line, so it's very easy to solve it. But for now, let's say this is something that we cannot find the answer immediately. Right. So any machine learning algorithm starts with a hypothesis, right? So we make an assumption that the output is connected by multiplying some parameter or some weight that we call here theta 1 by the input, which is X. And then we have to define a cost function or loss function, which measures how good or bad the parameter theta 1 is, given this data set that we have. So here we use something called mean squared error, right? So we're gonna subtract the predictions, right? So theta 1 times each input minus the actual output value or the Y value. And we take this to the power of 2. And now the goal is to find the theta 1, the value of theta 1 that leads to the minimum value of the cost function. And that's why here we are using arguments. So if you don't know what arguments here means, that we are not looking for the minimum value of the cost function, but indeed we are looking at what input value, which is here theta 1, leads to the minimum value of the function. So if we look at this cost function, this sort of like red quadratic function that we have here, we can obviously say that for theta 1 equals to 1, if we get to the minimum point of this function, which is exactly 0, which means that it's a perfect fit. And this is something that we knew because the slope of that 45-degree line is 1, right? But the problem is that what if this was more complex, right? What if you're trying to solve a problem that looks like this and now you want to find the minimum, right? So in calculus, you know that now you have problems with local minimums, also like we might have like local maximums and so on. So in order to these cases to solve the problem, one way to solve it is to look at the derivative of a function, right? So what is derivative? Derivative is the instantaneous rate of change, right? So let's say I want to find the minimum value of the cost function here, and I have some sort of like random guess that the solution is here at 1. So what you can do is that you can find the gradient, which is this sort of like pink line here that basically touches this function at this point, and see what the value of the derivative is, right? Is it positive or negative? So when the derivative is negative, like this point 1, this means that we have to go to right to find another point that leads to the, like a sort of like a smaller value of this function, right? So the question is that from point 1, should we go to right or left? So obviously here we should go to right, right? Because if we go towards left, then we are going to increase the value of the function rather than decreasing it, right? So that's why we now go to the point 2. And now at the point 2, again, we look at the derivative, which is this the yellow line, and you can see that still the slope of this line, right, is negative, which means that again we have to go towards right. And we're going to continue this process multiple times until we hopefully get close to the actual minimum value. And this is something that we're going to use a lot in deep learning and neural networks, because in many cases we cannot find the exact solution. So we start with some random guess, and then we try to get closer and closer to the minimum value. So this is like a general formula that we have. So this is the current value, this theta 1. And then we subtract something that we call learning rate. So this tells you how big each step is. And then we multiply this by the sort of like the derivative at that point. And recall that here we have this negative sign because we always have to go to the opposite direction, right? So that's how you can decrease the value of a function. So if derivative is positive, you have to go towards left. And then if derivative is negative, you have to go towards right. And so this is the general formula, and we can repeat this. So it's very easy to implement. The only thing that you need to know is the derivative, right? And in this case, as bonus, I have found or calculated the derivative for you guys. And you can see that, and one other thing also here I've done, I use n for the number of samples. So in this case, if we have, let's say 1000, we have a summation over 1000 data points. And in order to take the derivative of this term inside the summation, so think about it this way, I can call this whole term like, let's say z, and the derivative of z squared is 2 times z, right? Derivative of a polynomial function. And then if I apply chain rule, I have to take the derivative of z. So this means that I get 2 times z, and then the derivative of the inside term with respect to theta 1, which would be the constant next to it, which is xi. And this is also something important to keep in mind. When you find the derivative here of, for example, let's say cost function, the derivative with respect to the model parameters or weights, not the inputs and outputs. Inputs and outputs are given and they are fixed, so there is nothing to optimize for. And so you can see that we have the derivative here. One thing you need to keep in mind is that in order to find the derivative, let's say this n, the number of samples, is 1 million. You need to be able to have access to all of them. And that's not possible when you're working with large scale datasets. So I'm going to talk about this now more in the next slide. So in this slide, I'm going to talk about two things. So let's say now we have more than one sort of like weight or parameter, right? So let's say you have theta 1, and now you have theta 2, right? So in this case, now you can see that I cannot use derivative, right? Because derivative is respect to one parameter. So instead we have to use something called partial derivative, that we use this notation that we have here. So this is the partial derivative of the cost function with respect to theta 1, and this is the partial derivative with respect to theta 2 that for some reason disappeared here, but I just write it again. So that will be sort of like the partial derivatives. And I have one video, the one before this one, part 2, that I talk about partial derivatives if you want to learn more. But the goal here is that, if in this sort of like higher dimensional problem, I start at this point, how can I get closer and closer to the actual like minimum value, which is somewhere here, right? So like think of this as a bowl, and you want to get to the bottom of the bowl because that's where the minimum value is. So one good news is that we can use the update formula that we had before, so we can get our current solution. And now theta is actually a vector because we have two values for it, theta 1 and theta 2, and then minus some learning rate times the gradient. And remember, gradient is just a vector of all partial derivatives. So theta and its gradient, gradient of the cost function with respect to theta, they have exactly the same shape. So anyways, if we have defined a cost function, now as theta 1 and theta 2, we can find the gradient and we can use this update formula. Except that now we have a problem, as I said before, that if we have a lot of samples, we may not be able to compute the gradient for the entire data. So how can we solve this? We can divide the data into what we call as batches. So meaning that if this is all your data that we have, we now have these smaller batches, right? So for example, in this case, we have 1, 2, 3, 4, 5 batches. And we just find the gradient for this batch, and then we move on to the next one. And in each case, we are gonna update this parameter theta. And here, something that also happens is that once you basically go through the entire data, we call this one epoch, right? So you need to have 5 batches or 5 sort of like iterations to go through the entire data. And now you can repeat this process multiple times. Again, go through data one more time. And that's why here also it is common to shuffle the data, like sort of like has some use some sort of random permutation. And that's what we call it number of epochs. So to summarize this, we have 2 hyperparameters, meaning that parameters that we have to fix before even we start the training process. One is the size of minibatch, right? How many points you want to put in minibatch, and then how many times you want to go through the entire data. So that's what's called number of epochs. And now we are very much ready to talk about how we can put together a simple neural network in PyTorch. One other thing that we have to do is that also, because here I'm gonna work with sort of like a synthetic data, meaning that data that I generate myself, I need to first talk about how to create the data. But in practice, you are given a data set, right? So you don't create your own model. But the good thing here is that in this case, we can actually make sure that what we do, this analysis in this lecture, makes sense and it works because we have access to the underlying weights or parameters that we generated data from. So here we assume that the output is a linear combination of inputs with these weights that we call them W1 and W2. In the previous slide, I called them theta 1 and theta 2. So I intentionally use different names here because it doesn't really matter. It's just names of variables. And here I call them W1 and W2. And we have 2 input features, X1 and X2. And then we have a bias term. So this is like the general like framework for linear regression. And if you're familiar with linear algebra, you can write this as inner product between 2 vectors, one vector for the weights, W1 and W2, and the other one for the input features, or the sort of like which is part of the data set, X1 and X2. So I can write this in terms of like this inner product, right? Like X1 and X2 in the row of a vector, and then, or a matrix, and then W1 and W2 in the column of another matrix, right? And this can be easily generalized to cases that you have more than one sample, because we obviously cannot train a neural network with only one training example. We need usually like many training examples. And the way we can do this is that we can stack all these X1, X2, these features together in the rows of a matrix that we call this X. And this is usually what even you use in scikit-learn when you're working with traditional machine learning problems. So you have a matrix that each row corresponds to one sample or example, and each column corresponds to a feature. You multiply this by the sort of like the weight vector, which is W1 and W2, and then you add the bias term, right? So we start by importing PyTorch, that's import torch. And also I'm gonna import from torch.utils, I'm gonna import data. So this has a lot of things that we can use in the next slide to load the data when we cannot do the entire data once. So here we have this synthetic data function, right? So we are defining a function that we provide W and B and the number of examples. And now we want to have the number of examples that we specified generated using this formula, right? So what we are gonna do is that we're gonna generate a matrix of normal distribution with mean 0 and variance 1, and then we're gonna multiply these, right? So this is the matrix multiplication, torch.matmul, X and W, as you can see in this here. And then we add the bias term. The reason that this works by just adding a single scalar here is because of the broadcasting mechanism. So this means that this parameter B is going to be added to all the sort of like elements of the result of this multiplication. And then we always add some type of like, random noise, because if not, because we are working with linear regression here, you can just pick 2 points and draw a line that goes through them. So the problem is trivial. So we just want to add some noise. So the problem is not trivial. For example, as I said, if I have one point here and here, I can just draw a line. But if I add some noise to it, right? So this one now would be here, this one would be here. So now I cannot just draw like one line that goes through them. So now I have to look at the entire data set and figure out how it works best. So we did all these steps to generate the data set, but this is basically the function to generate the data set. Now we have to pass in two important arguments, which is the actual W, which is here 2 and negative 3.4, and the bias term, which is 4.2. So remember that here W1 and W2, I'll call them weights, and then B, I call it bias. And then the total number of samples. So let's say we want to generate 1000 samples. And I call these features and labels. So the features has the X values, so that's X, and label is Y. So I can look at the shape. So as you can see, my input data is 1000 by 2 because each sample has two features. And then the labels are 1000 by 1. So for each sample, I have one output value Y. Okay, so now we get to this important part, the reason that I import from torch.utils, I imported data. So it has something called like data.DataLoader. So what this does is that you give your entire data set here and the batch size that you have in mind. Remember, the batch size is that like how many samples you want to have access at each time. And this shuffle is here, like if you want to like randomly permute the sort of like the samples, so they are in different orders every time that you sort of like want to have another epoch. So here I put the batch size equals to 10, and I use this function that I just defined. I mean, it's just like one line technically. So what this does, this gives me an iteratable object, right? So this means that every time that I'm gonna call this data iter, what's gonna happen is that I'm gonna get 10 sort of like rows of the matrix X and the corresponding 10 elements from the vector Y. That sort of like means that 10 input output pairs, right? And so again, if I run this one more time, you see that now I get different result because what's happening now, I'm gonna have access to the other mini batch, right? So again, have this picture in your mind that when you're using this data loader, so you're gonna start from here. So that's the first thing that we see here. We get 10 examples, and then we get another 10 examples, and so on. So here we have 1000 samples total that we created, and we have batch size 10. So we have 100 different of these sort of like mini batches that we have to go through them for each epoch. Okay, so now let's talk about the interesting thing. So after you generate the data, and as I said, that's usually the part that the data is provided, so you don't have to generate it, is to define your neural network model. So if you look at this case, we have a very simple example. We have two inputs. These are like the rows of the matrix X, which we call them X1 and X2. We have two weights, W1 and W2. We use the linear combination, and usually there is that sort of like that bias term B that we don't plot it here, and then we compute the output. So how can we implement this? From Torch, we are gonna import NN. So NN stands for neural networks. And here we are using a simple, fully connected layer, meaning that everything is connected together. So we are gonna start with NN.sequential, because usually in this case we have these sequential layers. And then we are saying that we have this linear model that we have two neurons like in the input layer, and then we have one neuron in the output layer. So in reality, you want to probably have more neurons in between. So for example, you can say 2 and 2 and 1, but here again we have like two neurons here and then one neuron here. And when you create these, you can immediately have access to those weights and bias term that we have, right? So W1 and W2 and B. So because we want to have access to the first layer, so we're going to use net 0, right? So 0 basically for indexing is always the first element, right? So that's why we use that. And we use dot weight and dot bias, right? So you imagine the weight has two elements, the bias has one element. Something also is crucial to to consider here is that the requires grad is already set to true, because that's what we need in torch.autograd for automatic differentiation, right? Because we want to find the gradients, right, with respect to these parameters for the update later. So that's why the model is keep tracking them even from now on. We don't have to directly set them to be true. And one thing that you can do, also you can initialize them if you want, right? So we have net0.weight.data, and then when you say like .normal and then this underscore here, right? So this means that now you want to fill in these values with a normal or Gaussian distribution with mean 0 and variance 0.01, right? And the same thing here for the bias stem, we just want to fill that with 0, right? So that's for the initialization. That's that random guess that we talk about, that, right? So remember that cost function that we have, and we said that we're gonna start from here and then try to get to the minimum value. So that's what's happening here. We are initializing them, and then we're gonna have different steps as we go through the sort of like batches of data to update these parameters. And remember here, because you only have one layer, right? So this is the layer 1. If you look at it, if you use like index 1, which would be the second layer, you get this error message that the index 1 is out of range, right? So this is important to consider. Here you only have one layer, so that's why we only have net and then index at 0. If you use index 1 to get to the second layer, you immediately get an error message that there is no second layer. Well, now let's go to the third step. So the third step is to define the cost function that we said that we need, because in order to find the gradient, you need to have a cost function first. And then the optimizer. The reason that we also need to have an optimizer or an optimization algorithm is because there's so many different variants of gradient descent that I talk about it. So you probably noticed that I talk about the stochastic gradient descent, minibatch gradient descent. There are also more recent methods called like Adam and so on. So that's why you have to specify what kind of optimization you want to use. So for here, for the cost function, we use something called MSE loss, mean squared error loss. That's exactly, this is from the sort of like the documentation page of PyTorch, and you can see that it's just simply subtracting two terms, taking it to the power of 2, right? So that's why it's called a squared error, and then you take the sort of like the average if you want. You can see here you have like different options, and that's why I always recommend you to go through the documentation when you really want to make sure that what you're writing is doing what it's supposed to do. And then, so we call this loss, and then we define something else called trainer. So this is our optimizer, an optimization algorithm. This one is not inside the neural network or NN module, is actually under torch.optim.SGD. And you have to pass in the parameters that you have. So I use net.parameters. So this gives all the parameters, those weights and the bias. And you have to specify that learning rate, right? That we call it alpha before, right? How big each step should be. So these are at least the minimum things that you need, right? So the loss function and the optimizer that you need. And I have this picture here for you, so you can see like what net is referring to. So net is what we define as our neural network, and now we are saying net.parameters. So this includes both weights and bias. So the last step is now to do the actual training part. So the first thing that we need is the number of epochs. Remember that we said that when you go through the entire data once, that's one epoch, and usually we want to repeat this multiple times, right? So you divide the data into mini batches, you go through them, to go through the entire data, that's one batch, and then you repeat this. So we can write this very simple like for loop, right, for epoch in range of num epochs, right? So then we get 0, 1, and 2. That's how range works. And then for each epoch, we have to iterate over that data underscore iter that we created using that data loader, right? So this means that we're gonna just read only one mini batch. And the first thing you need to do is to find your loss function, right? So that's why we use that loss that we defined before. We compare the predictions made by your model, which is called net, by the actual output values. And then we go trainer.0grad. And the reason we do this is because PyTorch by default likes to accumulate the gradients, right? So we save them, as we talked about that in the previous lecture, in the in the gradient of vector, and then you just want to make sure that you empty that out so you don't accumulate gradients in this simple case that we don't have to do that. So that's why we use trainer.0grad, and after that we use this loss function dot backward. So that's the case you actually find the new gradient for this loss function, right? That's why we, before applying this, you have to make sure that that place that you store the gradient is empty, and then you find the gradient. And then finally, when you say trainer.step, means that you're gonna have that update formula that we had, and you're gonna update those parameters, right? We call them net.parameters in the previous slide. And then after each epoch, that's why you see that this line is outside of the inner for loop. You can look at your loss function on the training data, right? See how this net, this neural net that you have, sort of like performs in comparison with the actual outputs that we have, right? So you can see here that for each epoch, we are sort of like, reporting the values, which is really a small error here because this is a very simple synthetic data. And as I said before, at any point you can have access to those weights and biases that we have, right? So again, we are looking at the first layer, .weight, .data. And we can subtract the actual value here, because in this synthetic data, we know the true W that generated data, and subtract this by what the model has the most current update of that sort of like parameter. And the same thing with the bias term B. And you can see in both terms, we are getting results which are very close to the actual values. So overall, to just sort of like wrap this, we can see that after you import your data, right? So the only thing that you really need to do is to define the model. So that's your neural net that we use nn.sequential. And then you define the loss function, the optimizer, which we call it here trainer. And then you just can have like this for loop to go through the different mini batches that you have. Make sure that you empty out the gradient before actually computing it so they don't accumulate. And then after you find it, you just use .step to make the update. I hope you found this video useful, and please don't forget to like and subscribe and keep watching.